So this is number 7. A 50-gram ice cube can slide without friction up and down a 30-degree slope. The ice cube is pressed against a spring at the bottom of the slope, compressing the spring 10 centimeters. The spring constant is 25 Newton meters. So in part A, we have to look at when this ice cube is released from the spring, what total distance will it travel up the slope before reversing direction. So we have our givens. Mass is 50 grams. Theta is 30 degrees. And we have our spring, so our delta x spring is equal to 10 centimeters. And we have a spring constant K is equal to 25 Newton per meters. And now we're going to draw our picture. So our picture, we've got a spring. And we have our block. And this is a compressed spring. So what we're going to do is we're going to look at the center of the spring. And we know that when the spring is unstretched, we would have our block here. So this distance from here to here is going to be our delta x spring. And we know that further when it gets up the hill, so this is the hill that it's going up, right? It's going to come up to here, say. Right, so this is going to be our final height, and this is our starting height. So I'm going to make this height our 0. So this is going to be my y equals 0, and this is going to be my y final here. So the other thing I want to do is I want to draw my axes. So I'm going to say that this is the positive x direction and up is the positive y direction. And what I'm trying to find in part A is the total distance traveled. So I'm really looking for this distance. So this is going to be my delta x, which is different from my delta x spring. So the delta x spring is just the distance that the spring is compressed from its uncompressed state. So if the spring wasn't stretched or compressed, it would be there. And so because the box is pushing on it, it's compressed. And so this distance is my the amount that it's compressed, or my delta x spring. But delta x is the distance it goes up the hill. And then part B is if I have now a plastic cube instead, I have a coefficient of friction now that is 0.2, and I'm going to find how far. So I'm going to delta x again, but now with friction. So let's do A first. And this is an energy problem. So I'm going to write the energy initial is equal to my energy final. And my energy is going to be my U initial plus my kinetic energy initial. So this is gravitational potential energy, kinetic energy plus my spring potential energy is equal to my U final, gravitational potential energy plus K final plus my U spring final. Let's make this initial. And so here, this is going to be my mgy initial plus 1/2 mv initial squared plus 1/2 k delta x spring is equal to mgy final plus 1/2 mv final squared plus 1/2 k delta x spring final. So here I know I'm starting at my position here is 0, so this is going to be 0. I don't have an initial velocity. I do have my and so this should be squared. I do have my potential energy due to the spring. My mgy final, I have that. My mgv final, or my final velocity, is 0. It's not moving, and I have no spring compression or expansion here, so that's going to be 0. So I'm left with this term and this term. So I'm looking for yf, and that'll help me find my delta x. So I'm going to divide both sides by mg. And so I get y final is equal to k delta x spring squared over 2 mg. And when I plug in, I'm going to get 25 newtons per meter times 0.25 1 meters squared divided by 2 times 0.05 kilograms times 9.8 meters per second squared. And so my Y final is equal to 0.255 meters. Okay, so now I need to find now that I have Y final, I need to find my delta X here, so this distance. So really what I'm saying is, this is my theta, so here's my theta. This is also theta, this right here. So I'm looking at this triangle right here. So this angle is theta, which is 30 degrees. And so this is the triangle I'm using here. So this is going to be my Y final, this is my delta X. And so I know that sine theta is equal to Y final over delta X. So multiplying both sides by delta X, right, I get delta X times sine theta is equal to YF. And so delta X is equal to Y final over sine theta. So now delta X is equal to Y final over sine theta, which is 0.255. And sine of 30 degrees is a half. So divided by 1/2 is meters. So this is really like 0.255 times 2. And so that's 0.51 meters. So there, I've found part A. So my delta X is equal to 0.51 meters. Now to move on to B, I'm now adding in friction. So I'm going to start again with E initial is equal to E final. And I have mgy initial plus, well, let's back up for a second. So I have U, my potential, gravitational potential energy, so initial, plus my initial kinetic energy, plus my spring initial, plus any external work that's done on the system is equal to U final, gravitational potential energy final, plus kinetic energy final, plus my spring potential energy final, plus E thermal. And so this is where my friction piece is coming in. So remember that if I have my block, right, it's moving up this hill, and now there's friction here, so I need to think about what frictional force do I have. So I'm going to do a free body diagram, right? My normal force points this way, right? This is my X direction, so I'm just drawing it in there. This is my FG, and I now have this force of friction there. And so just drawing this, filling in the components, this right here is FG in the Y direction, right? I'm saying this is my X and this is my Y. So I know that my FGY is going to equal the normal force. And so we'll use that in just a minute and know that this is theta. We can figure this out using geometry, but if this is theta, then this is theta. So here I have mgy initial plus 1/2 mv initial squared plus 1/2 k delta x spring squared plus, and then this is 0, so I don't have that. And now I'm going to have mgy final plus 1/2 mv final squared plus 1/2 k delta x of the spring squared plus my force of friction, so times delta x. So this is the work, right, that's done. So my force of friction times delta x is the work done. As it goes up, it's taking energy out of the system due to friction. All right, so going back, I have no gravitational potential energy because my Y value, I set it equal to 0 there. Nothing's moving once it's at the bottom, when it's at the bottom. I still have my spring. This does not get crossed out, so we need that. We don't have, it stops at the top, so my velocity is 0. My spring is like uncompressed and not stretched, so that's 0. And I have this term. Okay, so I have 1/2 k delta x of my spring squared. Remember, this is not the same as this delta x. is equal to mgy final plus force of friction times delta x. Now what I'm going to do is, from the previous part of the problem, we learned that my y final, so right over here, my y final is equal to delta x sine theta. So I'm going to plug that in. So I'm going to plug in y final is equal to delta x sine theta. So 1/2 k delta x spring squared is equal to mg delta x sine theta. Plus, now for the force of friction, my force of friction is mu times the force of the normal. So we're going to go up here. Force of the normal is equal to Fgy, which is equal to mg cosine theta, because this is the adjacent side to my angle. And so this is my vector Fg, and this is the component in the y direction according to our coordinate system. So plugging that in, mg cosine theta, delta x. So delta x is what I'm looking for. So I need to group terms, right? So I'm going to say delta x. I also have an mg in both terms. So I'm going to have sine theta plus mu cosine theta. So I just factored here. Okay, and I'm looking for this. This is the delta x that I'm looking for. This is how far it goes up the hill now that there's friction. So delta, I'm going to divide this whole side by mg sine theta plus mu cosine theta and this whole side. So my delta x is going to equal 1/2 k delta x spring squared. So that's that term. And now I'm just dividing it by mg sine theta plus mu cosine theta. Okay, and now plugging in numbers, I get delta x is equal to 1/2 times 25 newtons per meter times 0.1 meters squared all over 0.05 kilograms times 9.8 meters per second squared times sine of 30, which is 1/2, plus, now my coefficient of friction is 0.2 times cosine of 30. So when I plug that all into my calculator, I get delta x is equal to 0.38 meters. And that should be less than the delta x that I found when there was no friction. So I can just compare. My delta x here is 0.51, and now with friction my delta x is 0.38, so that makes sense.